morning. I'm Sihem Amer-Yahia, and I'm going to tell you today about exploration pipelines. So I'll first talk about introduce exploration pipelines, and then I'll briefly summarize what we did in terms of evaluating those pipelines, and then I'll show a demo. The demo is going to be shown on Spotify data sets. In fact, the development has been done and fully completed on SDSS, but I thought I'd show you something that's a little different. But a link will be provided at the end of the presentation on the actual application on which the system is running on SDSS. So let me start then the presentation.
Exploration pipelines are joint work with Aurelien Personnaz and Yogi Patil at CNRS. So here we're concerned with the question of creating sequences of exploration operators for a particular application, and in particular to go through a large data set. So we define an item set as a set of items that are characterized by a conjunction of predicates. So here I'm showing an example of a set of galaxies, of 52 galaxies that are defined by a combination of redshift and other attributes that characterize these galaxies. So the set of operators we're considering to build our exploration pipelines are instances of a by-example operators that takes an item set and returns a set of item sets as a result of applying a particular operator. For example, the bifacet operator takes an item set and returns subsets that are where each subset is characterized by a distinct value of a given attribute, in this case, redshift. And the by-distribution operator takes as input an item set and returns a set of items, item sets that share similar value distributions for a certain number of attributes. So we put together Dora, the explorer, that learns a sequence of operators, an exploration pipeline, using deep reinforcement learning, and by defining a given reward function. For instance, a reward function could be defined to find a needle in a haystack. In the case of galaxies, finding green pea galaxies or yellow pointed galaxies. We can also define rewards for other applications of Dora. And I'm going to be showing you a demonstration of EDA for Sum, whose purpose is to summarize a big data set. Before that, I'll just summarize here our validation or evaluation framework, whose purpose is to hire subjects in an experiment where we want to validate exploration pipelines by measuring two kinds of metrics: human system interaction metrics, such as the average delay or the length of a pipeline, and also human self-evaluation metrics by means of questionnaires that ask subjects to evaluate the feeling of accomplishment or the mental demand of going through an exploration pipeline. Let's now look at a video of EDA for Sum.
Hello, I am Aurelien from CNRS, and I'm going to talk to you about EDA for Sum, a system allowing guided exploration of data summaries. This work was a collaboration with Brett Youngman from the MIT and Sihem Amer-Yahia from the CNRS. So it's generally understood that summarizing a data set means finding k individually uniform sets that are collectively diverse. The question we try to answer in this work is, how can we summarize a highly complex data set? Like in this example, how could we summarize it if there was tens or hundreds of different types of galaxies in this data set? Our proposal is multi-step summarization. Multi-step summarization consists in extending the results of a one-shot summarization algorithm with a summarization pipeline composed of successive summaries produced by set-based EDA operators. So a summarization pipeline is a sequence of exploration operators closed under set-based semantics. Each item set is defined by a conjunction of predicates. So we defined 4 operators that are implementations of by example, which means that each operator takes an item set as input and returns one or more item sets related to the input sets. So how does the system choose which summary to show the user at each step? We used 3 different measures. First, the uniformity, which indicates how similar the items are to each other in each item set. Then the diversity, which indicates how different the item sets are to each other. And finally, the novelty, which indicates how new the item sets are for the user. So we evaluated global utility as a weighted linear combination of those 3 measures. Based on this utility evaluation, we designed 2 possible action to pick the one resulting in the most useful summary at each step. The second one is an end-to-end policy generated by training deep reinforcement learning agents to maximize the cumulative utility of a summarization pipeline. Both those algorithms are usable in 3 guidance modes. Full guidance, where the system decides every aspect of the summarization pipeline. The partial mode, where the system suggests the next operator, but the user can intervene. And manual, where the user does not receive any kind of guidance. The system is currently working on 2 datasets, a subset of the Sloan Digital Sky Survey with 2.6 million galaxies, and a set of 232,000 tracks from Spotify. The scenarios in the demo will let the users experiment the features of the application while looking for highly uniform ground truth item sets. For ZSS, it will be galaxy classes from the Galaxy Zoo classification, and for Spotify, it will be the music genres. So let's take a look at the application. So this is the interface of EDA for Sum. In the current pipeline area, you see the current pipeline that has been executed so far with all the operators and the evaluation of the resulting summaries. In the current operator results, we can see the current summary with each item sets returned by the previous operator, the evaluation of the summary, and for each item set, the predicate, the uniformity, and the size of the item sets. Here we see that the 2 upper sets are ground truth item sets, since one is mostly opera songs and the other one is mostly classical songs. In the summarization mode area, we can pick the guidance mode, the summarization algorithm, and the weighting scheme for the utility calculation, depending whether the user wants to prioritize the novelty or mostly the uniformity and diversity. Then we have the operator selection area, where the user can decide the operator to execute and its attributes. So at each step, the model selected or the algorithm, in the case of top 1 sum, will pick the operator resulting in the most interesting summary for the next step. Here we see that the balanced novelty chooses a bifacet and balance on this set. If we pick another model, like increasing novelty, we see that the inference gives this set as input with bineighbors and energy attributes. So let's go back to balanced novelty and execute this one. Here we have the new summary resulting from this operator, and we can keep going on like this for as long as we want. So this was a very short demonstration of EDA for Sum. The application is available online, and the code is freely available on GitHub. Thank you for listening.
All right. Thank you.